as we wait for the other students, we can just start with the introduction of the topic that we are going to take up today, that is coordination chemistry. Okay, as the name suggests, coordination, it means that something is coordinated or attached to something else. Now, if I am talking about complex structures, then you may also think of something which are known as double salts. Double salts, one of which with which you've already worked, is nothing but your more salt. You have more salt, right? More salt, then you have more double salts also. We can talk about carnallite also. Yeah, potash alum also. So here you have different kinds of double salts. Let's compare double salts with your coordination compounds. Let me just put the formula for carnallite, that is KCl MgCl2 dot 6H2O. And this is more salt, is a very important salt in which you actually monitor the iron. You have FeSO4, then you have NH4 twice, SO4 dot 6H2O. This is your more salt. You can talk about more like you have here KCl and MgCl2 is carnallite. You can talk about potash alum also. These three examples are quoted in your book also. So that is why I just picked them up. KAl SO4 whole twice dot 12H2O. Okay, so now how are your double salts different than coordination compounds? Right now I haven't introduced any coordination compounds at all. And it is such a simple topic that whatever you see right now, and if you understand that, you will just be able to get and revise this chapter in about 15 to 20 minutes time. And I am not exaggerating. The basics are only just that you have to understand what is the composition or how these complex structures are like present and how are they different from other double salts. And then as we move today, let me have a recap of what we are going to do today. We'll try and look at this, understand their structure by first of all finding out how to name these coordination compounds. Alright, that will be the first thing. The second thing that we'll move on is to how to write down the formula. Alright, if you are given the name, how to write down the formula. The third thing that we can talk about is what are the different kinds of isomers that they can actually form or make. Then after isomerism, we can talk about, say, the valence bond theory. Valence bond theory you've already done for after doing atomic structure. So you are familiar with this valence bond theory, where you know different shapes and geometries will be assigned as per the hybridization. You remember we had done hybridization. So based on that, we can actually tell what is the hybridization and we can also predict the geometry. Then there are other theories also given for coordination compounds, like you have valence bond theory, you have crystal field theory, but apart from valence bond and crystal field theory, let me tell you there are more theories also. You have ligand field theory also, and you have molecular orbital theory also. All these theories are available, but what are mainly there in your course is VBT and crystal field theory. After that, we can talk about the stability constants of these complexes. We can throw light on these stabilities. And last but not least, we can talk about the applications. Anything that is left? Applications, in which we can talk about the magnetic behavior as well. Magnetic, electric behavior of these compounds very well. I repeat, what we are going today for you is that we are starting up with coordination compounds. In coordination compounds, you have some kind of a complex structure in which whatever metals generally belong to D blocks, but you can have metals of other groups, other parts of the periodic table also. What is the criteria? That they should have low-lying vacant orbitals. You know that orbitals, what are the orbitals? Say if you're talking about d orbitals, then you have dxy, dyz, dzx, what else? Dx square minus y square and dz square. All these orbitals are capable of accepting electron density from other molecules, ions, or say neutral systems, atoms. So here in this case what we have is you have a central metal atom surrounded by ligands. Alright, these are called ligands, whatever is like attached. Whatever is giving the kind of whatever is giving electron pair and forming a bond with the metal are generally known as ligands. We'll throw light more on them. And there is a central metal atom. This entire is the coordination sphere. Say now supposedly if you have an ion outside it, which is like possible, say if you have say an ion outside it, then in that case this will be some name of the compound, chloride. Just as you have, what do you call this, MgCl2? Magnesium chloride. Similarly, I am just giving you an information from the top. What will this be called? This will be called some kind of a name which is given to the complex chloride. Alright. Now what happens when this is put in solution is that this structure of the coordination complex, it will remain intact and the ions will be 2 plus charge on this plus 2 Cl minus. You get the point? So the property of the coordination compounds is that the coordination sphere remains absolutely intact. It does not lose its identity in aqueous media. Whereas for the double salts, what we have is double salts are also, you may say that this is also a very complicated formula to remember. What is more salt? FeSO4, NH4 twice, SO4 and dot 6H2O, where these are the water of crystallization. In this, the moment I add them to aqueous media, what will happen? Each of them is ionic in nature and it's a good electrolyte. And what is the property of electrolyte? It will completely get dissociated into its ions. So what will you get? You will get Fe2 plus, SO4 2 minus, plus 2NH4 plus, again SO4 2 minus and plus water, which is feebly ionized, so it will remain as water, very faintly. So what is happening to double salts? Double salts are completely losing their identity, whereas the coordination sphere remains intact. That is one very basic difference between what you've done till now and what we are going to do now in today's class. Carnallite again is a double salt. Here again you tell me the ions which will be formed. K plus plus Mg2 plus Cl minus, 3 Cl minus depending upon the ratio, plus 6H2O. Here for potash alum it will be K plus Al3 plus, you can just check it for yourself, K plus Al3 plus 2SO4 2 minus plus 12H2O. Alright, so you can actually get to know that this will completely lose its identity structure the moment it's put in aqueous media, because it will get dissociated into its ions. Whereas for the coordination compounds, what happens is for the coordination compounds, the sphere, the coordination sphere, whatever is there within the brackets will remain intact. Say for example, let me just take up an example and explain. If I talk about a complex, I haven't defined the coordination compound, so it's a little rude to talk about it. Say if I am giving you an example of this, then in that case what will be the ions formed on adding it to water? 4K plus FeCN6 4 minus. Do you get that? The charge is balanced accordingly. So it will form 4K plus FeCN6 4 minus plus, alright, 4 minus. Do you get that? 4K plus FeCN6 4 minus. Okay. Now before I rub it off, just for you, we are going to start with coordination compound today. Alright. Coordination compounds are a little complex, which have a central metal atom which may or may not be d orbital. Why d orbitals mainly? Why d block elements mainly? Because they have low lying vacant orbitals which can accept the electron density from other atoms, molecules or ions. What atoms, molecules or ions? It can be ligands, they are generally called ligands, but then they can be anions. Very rarely cations also are used, like you have NO plus and other types. You have neutral molecules like water, ammonia also, which can be actually contributing to the central metal atom. It is capable of accepting electron density, because low lying means low in energy, that the orbitals are low in energy. Alright, and this whatever is there within the square brackets is your coordination complex, and it remains intact even on adding water. Whatever is outside will get dissociated. So you have K4 FeCN6, so this will form 4K plus FeCN6 4 minus, that is like balancing the charge. But in case of double salts, what happens when we add the double salt like ferrous sulfate, ammonium sulfate 6H2O, which is nothing but your more salt, when we add this to water, it will completely lose its identity to form the respective ions. What will be the ion formed? Fe2 plus SO4 2 minus plus NH4 2 plus water, right, according to the ratio. So double salts lose their identity completely, but a special feature of coordination compounds is that they do not lose their identity. Then an important thing that was actually given or stated for the understanding of these coordination compounds was given by Werner. That is known as Alfred Werner. I should be calling him Sir Alfred Werner. He gave his Werner's coordination theory. You all are very brainy, so you must have got it, the understanding of this structure right by just looking at it. So look up and understand Werner's coordination. Yes. They have their p orbitals at a lower energy than the energies of the incoming electron pair which is like coming. See, if the energy is low, how do I put it? If I actually want to vacate a particular flow, alright, where will be the lowest energy? Right there at the bottom. So what will be the easiest thing to do? Go out to the balcony and just throw things. Where will it go? Straight away. The least energy required is to put it there and it will be stable at the ground floor. Alright? Do not compare it with material things. I am just talking about chemistry. Otherwise things will get broken. You getting the point? So it is easiest to come to the level which is the lowest in energy. And because anything which is low in energy would be willing to accept energy from the other elements which are capable of contributing. Okay, now let's talk about the Werner's coordination theory. A very simple example I have given already. Now I told you that the moment you add a coordination compound to water, whatever is outside, that will get dissociated. That means potassium was there outside, so it gets dissociated. So I got 4K plus and FeCN6, no need to write anything. Look up, no need to write, put your pens down. What you have here is you have 4K plus FeCN6 4 minus. These are known as the primary valence. Primary valence. Werner stated that there are two types of valencies. One is a primary valence and the other is the secondary valence which is available with coordination compounds. The primary valence is ionizable. Ionizable means whatever is capable of forming ions. So primary valence is ionizable, so it will form ions. What ions? You know, K plus and FeCN6 4 minus. So these are forming the ions. So this is like ionizable. This is primary valence. You understand that? So the primary valence in this case is like 4. If I talk about the secondary valence is it talks about those bonds or those number of atoms which are joined to the central metal atom which are non-ionizable, because you know that CN6 are still remaining attached to Fe. They are not getting dissociated to 6Cn minus. No. So they are remaining attached. So this is known as the secondary valence. What is this? Secondary valence. And the fourth point in Werner's coordination theory is that he stated that he stated that with the help of this coordination complex that you have, each of the ligands are arranged in such a fashion that there is a particular spatial arrangement. Like sp3 has a tetrahedral shape, you know. So each one of them will either be tetrahedral, square planar, octahedral, depending upon how the ligands are surrounding the central metal atom and which ligands are surrounding. Okay, learnt? Werner's coordination theory is simple. I repeat, you have coordination compounds. Coordination compounds have a special feature where the complex within the square brackets remain intact even on putting it in water. Alright, the moment we put it in water. But double salts dissociate completely. So they lose their identity. Werner actually worked with, I'll tell you how he worked with. He worked with COCl3 dot 6NH3, 6NH3, alright. He worked with this particular compound. Let me just check. COCl3 dot 6NH3, yes. He worked with this compound, alright. And because I already stated the coordination postulates, the coordination theories postulates. What are the postulates? Tell me again. There are two types of valencies, primary and secondary. Second point talks about primary valency. Now what are P? This is P. Primary valencies are ionizable. Alright. They are ionizable, and whatever is there outside the coordination sphere, don't write. Because I know you'll remember and then put it down in just 2-3 seconds. Then the secondary valency is non-ionizable. Alright. Because it is non-ionizable, matlab, ये जो अंदर वाला है, they are not getting dissociated. So primary valency is whatever is outside. Secondary valency is whatever is getting attached to the central atom here. So secondary valency here is being contributed by Cn minus. ठीक है? And what is the secondary and non-ionizable क्यों कह रहे हैं? Because Cn is not getting dissociated to, Cn is not getting separated from here as Cn minus. So this is non-ionizable. So how many secondary valence do you have here? 6. And this 6 is also known as the coordination number. This is also known as the coordination number. The secondary valence therefore is also known as the coordination number. And each of the coordination compounds has a particular shape or geometry that is actually designated by these ligands only. It has a, in other words, in Werner's statement, it says that each of the ligands is attached to the central metal atom according to some spatial arrangement. What is that spatial arrangement? It talks about the structure. And you know it very well that that's based on some kind of, we will be doing some kind of an arrangement which may be square planar, tetrahedral, octahedral. In that case, you can actually see central metal atom is, I will just talk about it. The question is very valid here. Can we have any coordination compound with two central metal atoms? If you actually have, here you have a, remember, like we've done till now in chemistry, we always put the cation first followed by the anion. This is what we actually have been doing. We always put the cation followed by an ion. So is the case in case of coordination compounds. We always put the cation followed by the anion. Say supposedly, if this was also a coordination sphere, K4 की जगह पे, if this carries 4 minus charge, I will put some coordination sphere with a 4 plus charge. That is also a possibility, right? So then in that case, let me just put randomly metal CO4, 6, anything. I'm just taking an example randomly. So then in that case, you say now there are two coordination sphere, but when you put them in water, it will get dissociated into this coordination sphere plus this coordination sphere. So one aspect of it is that you can have a double coordination sphere, coordination compound, where you have the anionic part also as the coordination sphere and the cationic part also as the coordination sphere. So there you can have more than one metal atom. Another possibility is that you talk about the bridged coordination compounds. That we'll just talk as we proceed. Let me just tell you what Werner did. See, you also can try it out and get something new like that in future. And I've been encouraging to do that because I know all of you all will continue with science. You have COCl3.6NH3, Werner, this is what he took. He found that when he added AgNO3 to it, what did he add? Silver nitrate. तो क्या होगा? There will be double kind of displacement and you may get a precipitate of AgCl. Right? You may get a precipitate of AgCl. Now when he took COCl3.6NH3, I want to listen to how he worked. When he worked with COCl3.6NH3, he got 3 moles of AgCl. When he added AgNO3, he got precipitates of AgCl. Do you get that? To this particular compound, he took COCl3.6NH3, he added to this AgNO3. तो कौन सा प्रेसिपिटेट बन रहा है, AgCl का, बट इस केस में ही गॉट 3 मोल्स. सो यू मे फील दैट ठीक है COCl3 है, 3 है, लेकिन द मोमेंट ही टुक COCl3.5NH3 देन ही गॉट 2 मोल्स. अभी भी Cl3 है, अमोनिया ही तो रिड्यूस हुआ है. एंड देन व्हेन ही एडेड COCl3.4NH3, this is available in 2 colors. So he tested it with both the colored solutions of these coordination complex compounds. So here he got only 1 mole. Do you understand that? I gave the theory before because now you will understand his work or experiment very well. He took this compound and altered. This is kind of, say, like ammonia is like added up as your water of crystallization is added up. So this is like kind of a solvent structure, solvent system which is playing a role. So he just kept altering the mole ratio of ammonia. What happens is CO, each metal has a fixed coordination number. Each metal has a fixed coordination number. What is this coordination number? This coordination number is, for a metal, is the number of ligands or ligands, whatever you call it, get attached to the metal atom. Okay, these are the numbers. So that is like fixed. For cobalt it is 6. For cobalt it is 6. So what happens in the first case? You get a coordination complex. This is how he gave his theory. Let me tell you, it's not that simple as you just go through. What he formed was CO, NH3, 6. This remained intact and you had C3. So how many ionizable ions now do you have? 3. So what do you get? You get CO, NH3, 6, 3 plus 3 Cl minus. Understood? So 3 Cl minus means that on adding AgNO3, how many moles of AgCl will you get? 3. Because 3 Cl minus are available, they will interact with 3 Ag plus to form 3 AgCl. So 3 moles. Next time what did he do? He reduced 1 mole of ammonia now. So what happens is the coordination number is 6. So if he reduces this to 5, but the coordination number needs to be satisfied. So one of the Cl will now satisfy, and what will happen outside? You have only Cl2. Okay. So now how many moles? You get 2 moles because these are the ionizable chloride ions. Primary valence. Okay. Then the next time, now you can tell it for yourself, this will be CO, NH3 4 times and now Cl2 within the coordination sphere dot Cl. So it gives only 1 mole. So you understand, this was the experiment that was performed by Werner, after which he gave this theory that each coordination complex has 2 types of valencies. One is a primary valence and the other is a secondary valence. Primary valence, the next point of his theory is that primary valence is ionizable, the one which gets dissociated into ions. So primary valence is whatever is outside the coordination sphere or the charge on the coordination sphere. Like if I separate it out, this will become 3 plus 3 Cl minus. So that is your primary valence. Okay. Now your secondary valence is something which is within the coordination sphere and is remaining attached to the central metal atom. Or in other words, secondary valence is contributed by something which are called as ligands, and these ligands can either be ions, they can be neutral molecules also, which are contributing the electron density towards the central metal atom. These are non-ionizable because they do not get dissociated or the coordination sphere does not lose its identity in aqueous media. These ligands or the number of ligands which are attached is known as the coordination number. So your secondary valence is equal to the coordination number. If I am saying CO has 6 ligands around it, so the coordination number of CO is 6. Coordination क्या होता है? The number of atoms just surrounding a particular atom, right? And then after that I did state that each coordination compound has a particular spatial arrangement of it along with ligands depending upon what kind of an environment or system is created.
We are saying that coordination number is the secondary. And if we
The outside chloride ions are only attached in an ionic fashion which are outside the coordination sphere. So they are not directly held together. That is why even when I show you the structure of, if I have to show you the structure of this only, just answering your doubt, that if you are talking about this, when you talk about Na plus and Cl minus in aqueous media, how do you show it? You show it as Na plus Cl minus, which is understood, so you do not actually show these like that. What happens is you have CO, NH3, directly linked to it are NH3. Alright, so this is direct linkage. Direct neighbors कौन है? Ammonia. And कितने हैं? 6. ठीक है? Now this is your coordination sphere, and then you have your 3Cl minus outside. उनका कोई orientation नहीं है, because your ionic bonding is always non-directional. So you cannot actually give it a direction and state that this is attached to it. You can simply say that this is one form of an ion and this is attached to your 3Cl minus. Or you show it as Cl3 also, that is also correct. Yes. They are connected. अब आप जब NaCl शो करते हो वो तो एक ही बॉन्ड है, तो उसको आप डायरेक्टली ऐसे शो कर देते हो, ठीक है. जब आप MgCl2 शो करते हो तो उसको डायरेक्टली ऐसे शो कर देते हो, पर उसके अंदर ऐसे तो नहीं करते कि नहीं MgCl2 ऐसे ही होना चाहिए. You never say that MgCl2 should be like linear or something else, because you know it is an ionic bond and ionic bonds are non-directional. तो जैसे मर्जी शो कर दो इसको. अगर आपको बुक का फॉर्म नहीं पसंद में आता तो शो कर दो बाहर 3Cl है, कहीं से भी इधर उधर अटैच कर दो बाहर, but it should be outside the coordination sphere. We are not exactly attaching it, but it has a linkage to it. The first is being provided by this, and the second coordination is being provided by your Cl atoms, which are ionizable because they are outside the coordination sphere. Okay, it is very easy to replace them, but not that easy to replace these. So I mean, you can do it by using certain specific chemical reactions, but these are the ionizable ones and these are the non-ionizable ones. This is your primary valence, this forms your secondary valence. Yeah, because that is why, because generally they are like directional, and here you have a particular bonding in a particular character, but we do not talk of ionic and covalent now more or less, because this is a separate class, coordination compounds, which is like complex structures in comparison to the normal ones. So easily it's very difficult to break them, and that is why, because they form a very stable complex. कब नहीं टूटेगा ये coordination sphere? क्यों नहीं टूटेगा? Because it is highly stable, and if it is going to be stable, then only it is difficult to break these bonds. अगर easy होता तो they would also have been as good as your double salts, right? So that is why it is given with a lot of importance in your texts also, that double salts are different than your coordination compounds. Okay, then I think we can now move on to say the class explaining of the coordination compounds in general. See, I've already talked about the coordination compounds have a central metal atom. That central metal atom, the very first thing is that you should be talking about the central metal atom. This central metal atom should have low-lying orbitals which are capable of accepting electron density. I have repeated it so many times. Generally, D block elements are selected because D block elements ka size is small and they are capable of actually holding the incoming ligands tightly. So small size, high charge density and low-lying orbitals all contribute to the fact that D block, you will be doing DNF also, you haven't done it yet here. So this is what is contributing for the D block elements to be a major part of the coordination compounds. Otherwise, you have other elements also available from other parts of the periodic table as an exception, but provided it is important that they should be having low-lying vacant orbitals. Okay, then we talk about, say, and always remember that they have a fixed coordination number. Now when I say coordination number means that I am talking about the secondary valence. The secondary valence is generally fixed for a particular metal atom. Like for nickel it is generally 4, for cobalt it is generally 6. So it all depends. Then fixed coordination number, and they have a particular they are arranged in a particular spatial form. That means the arrangement is also fixed. Once your coordination number is attached, your arrangement is also according to the hybridization that we can talk of very soon. Now what are ligands? Ligands are the ones which are contributing as the coordination number. They are the atoms or ions which are attached, which are bound to the central metal atom, Now here, just look up, because we are just introducing, we can talk about different types of ligands. Central metal atom तो आपको समझ में आ गया. It can be nickel, it can be iron, it can be cobalt, platinum, many more. So you have understood that what the properties of the central metal atom are. It's basically the center of your coordination compounds. Ligands are the ones which are bound to it. So अब ligands कितने type के होते हैं? You can have depending upon वो कितनी site से contribute कर रहे हैं. Like if they have only one site, you call them monodentate ligands. Monodentate ligands. Monodentate. Dentate or denticity refers to the points of attachment. Like for example, look up, all of this in more is like given, so it is more important that you understand it first. Monodentate जैसे OH minus है, ठीक है, जैसे CN minus है. So I know it will attach only from the carbon side to my metal, so it can be CN minus, or it can get attached from the N side also, but not from N and C together. So you talk about them, I will talk about it later. OH minus है, CN minus है, you can have more say Cl minus, फिर chloride हो, you have chloride, bromide, iodide, fluoride, all such kind of ions are contributing only from one point. So they will attach only from one atom, from one atom side. So these are called monodentate ligands. Now there are something which is called as bidentate or didentate ligands also. It's written as didentate ligands. Didentate का मतलब अब क्या हो गया कि वो दो तरफ से contribute कर सकते हैं, ठीक है. इसमें तो NO2 minus is also monodentate. Or examples we'll do a lot while practicing questions. Bidentate ligands में क्या है, they will have now 2 points of attachment. One example is that of ethylene diamine, normally written as EN. This is ethylene diamine. ऊपर देख के पहले समझ लो इसको, क्योंकि ये structures दो ही important हैं सबसे ज़्यादा. Ligands which are polydentate, which are like more than one, which have more than one denticity. Didentate मतलब दो points of attachments हैं. अब कहाँ से, जैसे अगर इथिलीन डायमीन की हम बात कर रहे हैं, सो इथिलीन इज योर इथ, दो कार्बन. डायमीन आपको पता है कि नॉर्मली कार्बन की वैलेंसी कितनी होती है, 4. सो H CH H 1 2 3 डायमीन है ना. सो एक NH2 इधर और एक NH2 इधर, ठीक है. So this is your NH2 and NH2. So this is ethylene diamine. Okay, ethylene diamine. और इसमें इस नाइट्रोजन के पास भी लोन पेयर है देने के लिए, और इस नाइट्रोजन के पास भी लोन पेयर है देने के लिए. So at one point in time when it is getting attached to the central metal atom, it can contribute from two sides. Clear? It can get attached from two sides. So this is ethylene diamine. Got it? So that is why this is didentate, क्योंकि एक ही compound को attach होते time it can get attached from 2 points. Like for example, अगर मेरे को metal में ethylene diamine is one of the ligands, then you generally show it as, books में you will find it as EN and EN. इसका मतलब क्या है, समझ लो कि ये एक NH2 से, क्योंकि एक N के पास लोन पेयर है तो एक यहाँ से अटैच हो रहा है, फिर CH2 तो बीच में ऐसे ही है, and then you have NH2. So एक ही बारी में it has got attached. That is why ethylene diamine is shown as this. Short form is written as EN, and you have ethylene diamine getting attached from two nitrogens like this. Structure याद हो गया? What is ethylene diamine? NH2, CH2, CH2, NH2. Learnt? So then you can have another one. एक और bidentate. ये इसीलिए मैंने अलग से समझाया because ये थोड़ा सा new है to you. You haven't done organic yet, so it's like done. Then we talk about oxalate ion. Oxalate ion क्या होता है? Oxalic acid होता है COOH, COOH. What is this? Oxalic acid. ठीक है, ऑक्जेलेट आयन जो है दोनों H हटा दोगे H प्लस, तो ये भी माइनस हो जाएगा, ये भी माइनस हो जाएगा. ऑलराइट, सो ऑक्जेलेट आयन इज योर COO माइनस, carbon is attached here, COO minus. So again it has 2 points of attachment and it can get attached to the central metal atom like this. दोनों एक ही बारी में they are bound to the central atom. Another thing is, please make sure that you know their forms also, other forms. This is C2O4 2 minus. This is C2O4 2 minus. So this oxalate can also act as a ligand, which is didentate. Okay. Then we can talk about other types of ligands also. You can have a polydentate ligand also. Polydentate ligand में just look up the most important example that you are doing is that of a hexadentate. Hexa means कितने points of attachment है ना? 6. अब सिर्फ ध्यान से देखना, सबको didentate ethylene diamine समझ में आया? फॉर्मूला बताओ, मैं भूल गई. ठीक है, this is your didentate because why? Because it has 2 points of attachment, one from this nitrogen and the other from the other nitrogen. Now when we talk about another ligand which is like very important is EDTA. What is this? Ethylene diamine tetraacetate. Repeat it now. Ethylene diamine tetraacetate. Louder. Louder so that I don't have to speak it again. Ethylene diamine tetraacetate. Right. So now here ethylene diamine तो हमारा यही है, तो यही है ethylene diamine, but tetraacetate. एसिटेट क्या कहाँ से आएगा? हमारा एसिटिक एसिड क्या होता है पहले ये समझोगे? CH3 COOH. ठीक है, अब इसका H प्लस हटाऊंगी तो ये क्या बन गया? एसिटेट आयन. अंडरस्टैंड दैट? CH3 COOH is your acetic acid. When I remove the H, it becomes CH3 COO minus, which is acetate ion. अब इसको यहाँ अटैच होना है, ठीक है, क्योंकि ये इस नाइट्रोजन के पास 2 हाइड्रोजन हैं इधर और इधर. ठीक है, अब इसको अटैच करने के लिए लेट मी टेल यू दिस यू विल डू इन ऑर्गेनिक. दिस हाइड्रोजन इज जनरली क्लीव्ड. यू हैव CH2 and H here. ठीक है, now what will happen here? This H plus will be lost and you will have the CH2 COO minus getting attached here. The alpha hydrogen, the hydrogen which is here at CH3, that goes off. तो अब हमारा acetate ion क्या लगा? CH2 COO minus. गलती से CH3 मत लिख देना because that will spoil the valency. कैसे? C एक तरफ से नाइट्रोजन को अटैच हुआ, H 1 2 3 4 CO minus. Got the point? H. No, I am not talking about. I am just explaining the structure, not the reaction. Now here, this will get removed off. You using ethylene diamine, you can always create your ethylene diamine tetraacetate by making it react with acetic acid. This is just a vague way. But ऐसे थोड़ी आपने ethylene diamine लिया, उसमें acetic acid डाला, फट से बन गया. You need to have more conditions to it. ठीक है, तो इसीलिए it is not direct. अगर पेपर पे करना आसान है, पेपर पे बनाते रहो जो बनाना है, जब तक रियलिटी में नहीं बनेगा तब तक उसका कोई फायदा नहीं है. ठीक है, what you have here is, so now I was explaining ethylene diamine, you understand is CH2 CH2 NH2 NH2. अब यहाँ पे 2 हाइड्रोजन की जगह पे we have the acetate ion. So you have CH2 COO minus CH2 COO minus टेट्रा है, टेट्रा एसिटेट, सो बाकी के दो हाइड्रोजन भी हटाओ, सो यू हैव CH2COO minus and then again you have CH2COO minus. Now this is ethylene diamine tetra acetate, and otherwise what is your acetate ion? CH3COO minus. अटैच करते टाइम एक हाइड्रोजन तो हटाना पड़ेगा ना, बिकॉज वैलेंसी ऑफ कार्बन शुड बी satisfied, so it will be CH2CO. So this is just only to explain the structure. And what is the denticity? Now see, minus हर जगह से माइनस जहाँ पे है तो it can contribute from that side. So you have minus ये 2, 3, 4, 5 and 6. So this is a hexadentate ligand which is very important. इथिलीन डायमीन टेट्रा एसिटेट, और एक बारी में जब ये मेटल के साथ इंटरैक्ट करता है तो ये हर तरफ से अटैच हो जाता है. घबराने की जरूरत नहीं है, स्ट्रक्चर कोर्स में नहीं आएगा, मतलब एक ही बारी में 6 के 6 गेट्स अटैच्ड. The orientation is not like this, but it is arranged in such a fashion that there is minimum repulsion. If you ask me, I will tell at the end of the completion of the chapter as to how to draw the structure, but it is only for those who are interested. Otherwise, इसका structure draw करना नहीं है. Yes. We are not talking about the preparation. I was just telling you that ethylene diamine tetraacetate is just an extended structural formula of your ethylene diamine. So that is why I told you that instead of those two H, you have just the acetate ion coming in place of that. Otherwise, what is the reaction you will have? Say, in order to prepare ethylene diamine tetraacetate, there may be a number of reactant molecules which may be involved. So that depends upon that. Maybe you are adding some kind of a chloride also which is abstracting H from here as well as an H from acetate, because it is also losing its H plus. Or you may be adding an OH minus, a base, but a base will not abstract an ion from here because NH2 is already a base. So it depends on what conditions are created. Keep thinking like that even after 12th standard. So, got it? So ethylene diamine is NH2 CH2 CH2 NH2, and this is a hexadentate ligand which you now understand कि ethylene diamine के दो हाइड्रोजन दोनों साइड से हटाओ और वहाँ पे 4 acetate लगा दो, so that becomes tetraacetate. That is a hexadentate now ligand. Alright, you can have more types of ligands also. What are those types of ligands? I'll just talk about them. You can have ambident ligands also. Ambident ligands. Ambident ligands होते हैं जिनके पास दो points of attachment है. जैसे for example you have Cn minus, or it can also get attached as Nc minus. So it can either attach from the carbon side or from the nitrogen side. You can have NO2 minus or ONO minus. NO2 minus में it gets attached from the nitrogen side, ONO minus में it gets attached from the oxygen side. You can have SCN minus or CNS minus. Alright, then you can have more also, you can talk about them. NO2, CN minus, NC minus. So ambident, and remember all these minus charges, whatever has a negative charge means it has already gained electron density, so it is electron rich. I don't know, but if when we did organic, I must have introduced you to something which are known as nucleophiles, because this same knowledge will be required later. These are also known as ambident nucleophiles. Whatever anions have 2 points of attachment, the ones which have 2 points of attachment are known as ambident nucleophiles. Here in this case we are calling them ambident ligands. Why? Because we need to specify कि कौन से point of attachment से it is attaching to the central metal atom. So these are your ambident ligands. Alright. Then now we can straight away talk about naming or the nomenclature of the coordination compounds. when we talk about the nomenclature of the coordination compounds, there are certain things that you need to remember, that the coordination compound, in the coordination compound, the central metal atom is always the secondary valence. The secondary valence is always counted by the number of sigma bonds which are formed, right? Please remember that when I am talking about the central metal atom, I am talking about certain ligands surrounding it also. I am talking about certain ligands also which are surrounding it. Now here in this case, these ligands, what is the secondary valence for this metal atom? 6. If I am just talking about this coordination complex. So secondary valence is 6. Now here, remember that the secondary valence will always be counted by the number of sigma bonds. Even if there is a pi bond formation, you will ignore that. The secondary valence will only be the total number of atoms or ions which are around it. Alright, another thing is whatever is there outside is ionizable. That you know. Alright, and one important thing is you also talk of the oxidation of the central metal atom. That we can just talk, because you know how to find out the oxidation state of Mn here. You know all of you all know how to find out the oxidation state. You know it is K is +1, oxidation state of Mn will be +x, O is -2, so -8 is equal to 0. Why 0? Because the total molecule is like balanced. So you have x is equal to +7. And now let me tell you, this is again kind of a coordination complex where you have K plus MnO4 minus some kind. So just understand that now MnO4, otherwise Mn also should have got dissociated from O2 minus. So you have K plus and MnO4 minus, and here your Mn is in what oxidation state? +7. So you should be knowing as to how do you calculate. K को बाहर ionizable valence को हटा दो तो coordination sphere पे एक charge आता है, that's -1. Then take it as x minus 8 is equal to -1. So x becomes equal to +7. So you should be able, I think you all can do it very well. You should be able to find out the oxidation state of the central metal atom also. Okay, now after that let's talk about the name. Before I talk about the naming, let me tell you that these complexes also can be of two types. You can either have homoleptic complexes or you can have heteroleptic complexes. What are homoleptic complexes? Homoleptic complexes are the ones where you have homoleptic complexes are the ones where you have same type of ligand which is attached. Like for example, CO NH3 6 3+, homoleptic. ठीक है? This will be homoleptic. Then you can also have CO NH3 say 4 Cl2 plus. This will be now heteroleptic. Why? Because you have more than one types of ligands which are attached to the central metal atom. So homoleptic complexes and heteroleptic complexes. Homoleptic which have the same types of ligands, and heteroleptic where you have different types of ligands. Okay. Then, so now let's talk about the naming now. Remember that whenever we talk of the coordination, please understand the naming if you're done with it. I revise for whatever we've done till now. We are going a little slow. We've talked about coordination complexes, which are coordination compounds bound in some kind of a sphere. We generally show it on paper by putting it in square brackets. So whatever remains within the square brackets remain intact. It remains intact. That also has a particular geometry that we'll talk about towards the end of the class. It has a particular geometry. Then the second thing is whatever is outside the coordination sphere is your primary valence. Whatever is inside is your secondary valence. So you understand Werner's coordination theory that there are two types of valence: primary ionizable, secondary non-ionizable. What is coordination number? It is secondary valence. And then the fourth point talks about the spatial arrangement of your structure. After that we started talking about explanation of the coordination compounds. Sphere के अंदर सब intact है. Central metal atom की property ये होनी चाहिए that it should be lying lower in energy and should have vacant orbitals. Low energy के बाद it should have also vacant orbitals to accept. होता क्या है vacant orbitals, मान लो अगर 3D is like fully 3D5 भी है अगर, ठीक है, अगर मेरे पास कोई configuration है in which I have 3D5 1 2 3 4 and 5, alright. 3D5, don't go by my structures, draw it properly. Diagrams. So you have 3D5 here, ठीक है, 5 मतलब 5, so ये तो filled है, कहाँ से lone pair लेगा? Let me tell you, एक property in coordination metal atoms की है that they are accepting lone pair, okay. Then 3D के बाद क्या आता है? 4s, 4p and 4d. मान लो ये अगर नहीं भी है इसके पास जगह टू एक्सेप्ट अ लोन पेयर. लोन पेयर क्यों बोल रही हूँ मैं? जैसे हमने NH2 की बात करी तो NH2 माइनस माइनस कैरीज, माइनस चार्ज कैरीज द लोन पेयर. It is not a single electron. It is not a that kind of a bond. It is a proper lone pair. So it should be requiring one full orbital. इसको एक पूरा खाली orbital चाहिए. तो इसीलिए it should have vacant low-lying orbitals. Okay. Then another thing. या तो 3D2 होता तो 3D2 में these would have been like 1 and 2, तो these also would have been available. Pairing होती अगर मान लो इनमें तो भी you would have had available. But अगर 3D completely भी filled है with a single electron, but then you will have 4s, 4p and 4d also available for bonding to form the coordination compound. Okay. Then after that ma'am, is it necessary to attach a single molecule to the EDTA? Can we attach 6 different molecules for 6 different sites? See, when you're talking about coordination compounds, you primarily talk about one central atom in one coordination sphere. Alright, there can be only one king in one palace. You understand that thing? So, you will have one central metal atom, and if now EDTA is attached to it, that means EDTA is contributing from 6 different sites. Get that point? And that will form a highly stable complex, and that will form kind of a ring structure. Now that you've asked this question, let me just talk about what is your EDTA. You now understand? सबके दिमाग में उसका structure है ethylene diamine would tetraacetate. So you have M. You know that N will be a point of attachment. Then attachment points मैं पहले लगा देती हूँ. It will be easy to draw the structure. Then you have COO minus. So you have COO minus, then you here have COO minus, and you have COO minus and COO minus. Points of attachment तो यही है. What is it? Ethylene diamine. हो गया ethylene diamine. Now tetraacetate means that this is one acetate. What is one acetate? CH2 COO minus. Another acetate will be CH2 CO minus. Another acetate will be CH2 CO minus and another acetate will be CH2 CO minus. मैंने सिर्फ उसी structure को rearrange करके लिखा है. Do you understand that? So you will have only one metal atom and not 6 metal atoms to join at 6 different sites. Okay? So that one metal atom is now attached from, it is being contributed by 6 sites by EDTA. कैसे? आपको मैंने बोला था nitrogen will contribute. This nitrogen will contribute, CO minus will be attached, then you have CO minus again coming here, this and this. So now do you get it? It's forming so many rings, and greater the number of rings, it's some kind of a chelate structure, chelation, or some people even call them chelates. So chelates. So this ring kind of structures, wherever they are formed, they are more stable. That is why ethylene diamine also forms a ring kind of a structure. How was it shown? You are shown the metal and then you are shown an EN like this. So it forms a ring kind of a structure. कैसे? You know it very well that you will have an N here and an N here, बीच में CH2 and NH2 and NH2 on the other side. So it will also form. So wherever you get a ring formation, there the stability of that complex is very, very, very high. So the metal EDTA complex looks like this, and the stability is very high because of a stable ring formation. You have so many ring structures getting formed here. So this is like kind of a chelation where you're getting close kind of structures. Yeah, because you talk about the chelation to be like something which is more than the normal bond. So wherever you have more than one bonds, then in that case you are bound to have a kind of a ring. So now while revising, we were talking about the coordination compounds, the central metal atom. The central metal atom should always be low lying and should be small in size and should have high charge density. Small size, high charge density, low lying, vacant orbitals. D orbitals बोलो अगर D block के लिए बोल रहे हो तो. Ambidentate नहीं, they have only one point, they are monodentate. ठीक है. The question is whether ambident nucleophiles can be didentate, because C and N both are capable of contributing, but they are monodentate in character. That means एक बारी में एक ही point of attachment होगा. ठीक है. Now where was I? Central atom हो गया. Then we did talk about ligands. Ligands में we did state that depending upon the sites available for contribution, you will have denticity. Denticity of OH minus is? Say it in chorus. Denticity of NO2 minus is? Say it in chorus. कोई coordination नहीं है. Denticity of Cl minus is? Denticity of oxalate ion is? Didentate. So it is 2. Denticity of ethylene diamine is 2. Denticity of SO4 2 minus is denticity of is again denticity of SO4 2 minus will again be 2. Denticity of EDTA is सोच के बोल रहा हूँ. Denticity of EDTA is 6. What are homoleptic complexes जिसमें same type of ligand हो? What are heteroleptic complexes जिसमें different types of ligands हो? अब सिर्फ ध्यान से सुनना, क्योंकि applications is what is asked. Rules for naming and nomenclature are not asked. Just as we name in a normal ionic compound, cation first, anion after that. Here in coordination also we will be naming cation first and anion later. Like for example, if I have K4 FeCN6, so पहला नाम जो होगा that will be for potassium. ठीक है? That will be for potassium. And if say I have CONH3 6 times Cl3, so this will be whatever you have a name of the coordination. So we will name the coordination sphere first, followed by the anion which is chloride. Why not trichloride and only chloride? Because MgCl2 को क्या बुलाते हो? Magnesium dichloride. It is magnesium chloride. You call, take any other example, say H2SO4, what is that? Hydrogen sulfate. Sulfuric acid is the common name, we hardly talk. Say K2SO4. So dipotassium sulfate तो नहीं बोलते हम, we call it potassium sulfate. So whatever is ionizable will not have any prefix. Whatever is ionizable will not have any prefix. Prefix मतलब tetra नहीं बोलेंगे उसको, tetra potassium. We'll just call it potassium. And whatever again here is ionizable is Cl minus are ionizable here. So we'll not call it trichloride. This is only chloride. ठीक है, ये चीज clear है. Central metal atom पे आते हैं. Let me just go stepwise according to the protocol which is given. Cation is named first in both positively and negatively charged complexes. This is, what is the charge on the complex? Negative. So this is a negatively charged complex. And what is the charge on this complex? Positive. So cation is named first whether it is a negatively charged complex or a positively charged complex. Ligands will be named in alphabetical order. Any doubts? Alphabetical order you all know. ठीक है. Anionic ligands will be named in O. सिर्फ O लगाने और कुछ नहीं करना. So इसीलिए पहले we used to give a chart. Earlier when I was a student, we were given normally a chart, alright, to learn the names of the anions, which you should also go through. Like, but it's very simple. You have Cl minus. What is the name of this ion? Chloride. So this will be called chlorido. What is this? NO2 minus nitrite. So nitrito. Okay, what is this? Oxalate. So the ligand will be named as oxalato. With some, if you have a neutral ligand, then the neutral ligand will be named as such. Jaise you have H2O. This will not be named as high. In some cases it may be called as hydro also, but generally named as aqua or aquo. Aqua and aqua both are like that. Then CO is named as carbonyl. Neutral ligands का नाम as it is रहता है, carbonyl. NO is named as nitrosyl. ठीक है, as a ligand, carbonyl, nitrosyl. Okay. This is your ammonia, but when it is a ligand, it is known as an amine with a double M. Amine with a double M. This is your now, you tell me, aqua. This is carbonyl, nitrosyl. Alright, then after that, if we have a positively charged ligand like NO plus. So the positively charged ligands are, they end in EM, IUM, EM. So if this is like a nitroso compound, NO is generally a nitro. So this will be called a nitronium. I'll just check it. Nitronium, I think. I do not have it in it. So it will be named as nitronium. We'll take up some example in which there is an NO. Nitrosonium. This is nitroso. And you have, so this is nitrosonium. Nitrosonium. That is what is given here. Alright? ठीक है, लिगेंड को नेम करना आ गया. जो भी अंदर होगा उसमें अल्फाबेटिकल ऑर्डर फॉलो करेंगे. अल्फाबेटिकल ऑर्डर फॉलो करने के बाद उन लिगेंड्स को we'll actually put a prefix before these ligands. The prefix का alphabetical order नहीं follow करेंगे. We'll follow the alphabetical order of the names of these ligands. Chlorido, NH2 minus will be this will be like amido, amino with a single M. Alright. Then you have chlorido, nitrito. Then you have oxalato and so on. Here you have amine, aqua, carbonyl, nitrosyl. Now here you will have nitrosonium, and if there is any other example with a positive charge, it will be ending in CONH2. Generally amide is CONH2. Because in certain cases when NH2 is there in a bridge, then also you call it amido. We'll check up examples to just confirm that. Alright, so then here you have different examples for this. After that, I was talking about that you actually prefix them with the number of, the number which is associated with them, which is put as a subscript here. Like this will be hexaamine, HEXA, and then complete amine will be written. Alright, this will be hexacyano. So that ways it will be having a prefix. Again, clear to everyone? And then after that, first your ligands are named. First always your ligands are named, and then comes the turn of the central metal atom. First always the ligands are named, like here in this case it will be hexaamine with a double M. Hexaamine, I'm sorry, because ammonia is like neutral. Hexaamine cobalt. Now the name comes for the metal after that. If I name it as, I have taken the simplest example, hexaamine. Alright, then you have cobalt, because all the coordination spheres generally written together. Cobalt. Now the name of the metal also depends upon whether there is a positive charge, neutral charge, or a negative charge on it. If there is a positive charge or a neutral charge on your coordination sphere, then the name of the metal atom remains the same. अगर positive या neutral है तो cobalt का cobalt रहेगा. अगर negative charge आता है तो it would have द नेम एंडिंग विथ 8, ठीक है. सो उसको हम फिर कहेंगे, अगर ये नेगेटिव होता कोबाल्टेट. जैसे इस केस में दिस इज अ नेगेटिवली चार्ज आयन, सो आई विल नेम इट एज हेक्सासाइनो पोटेशियम. आई विल टॉक अबाउट लेटर, just concentrating on this hexacyano, and you will have 4 minus. Now because it has a negative charge on it, it will be known as ferrate. For iron, it's according to the name that it has, ferrous, so it is known as ferrate. If you talk about gold, it will be known as aurate. If you talk about, and अगर normal नाम होगा, अगर आयरन के किसी कोऑर्डिनेशन स्फीयर पे पॉजिटिव या न्यूट्रल चार्ज होगा, you will just put the name as iron, okay, and if there is a negative charge then you will be naming it as ferrate. गोल्ड पे नॉर्मल चार्ज होगा तो नॉर्मल गोल्ड, ऑलराइट. अगर नेगेटिव चार्ज होगा तो ऑरेट, दिस विल बी आर्जेंटेट एंड सो ऑन. जैसे Ag सिल्वर will be known as argentate. So let me just try and give you some examples on my own before I proceed, and then we'll do some questions for say about whatever is possible. Here, say if I look onto the board first, say if I talk about this Werner's compounds with which he worked, CaNH3, 3Cl3, NH3 4, Cl2, Cl. If I have to name this, first of all, I know this is chlorido, this is amine, whatever, with a double M. What comes first? A comes first. So we'll have, starting, the first letter is generally capital. So this will be tetraamine. Remember, don't put an amino here, that will change the meaning. So double M, amine, dichlorido, now cobalt, or so cation is named, that is your coordination sphere, and then you have chloride. So this is kind of the name done, but you are supposed to put the oxidation state of the central metal atom after it, then leave a space and put the name of the anion. Okay, so in this case you find out the oxidation state of cobalt, that will be X plus 0, because ammonia is like neutral, minus 2 is equal to plus 1. Why? Because Cl has a minus charge, so this will have a charge of plus 1. So what will be the oxidation state of CO? It will be plus 3, and this 3 has to be indicated in the brackets in Roman numerals. So all of you all know that this is written as this 3. And you do not have to go into the entire maths chapter for knowing your Roman numbers L, C, etc., because the oxidation states are generally small. They are not that big that you need the entire mathematical concept of the Roman numerals, which you should know otherwise. Okay? So let's move on to some more examples. Tetraamine, dichlorido, cobalt 3 chloride. One more. We can also talk about, say, the names of bridged compounds. There are simple वाले तो कर लोगे, ठीक है. I'll give you some questions to try it out, because सब बड़े अच्छे से yes बोल रहे हो, ठीक है. Tetraamine, dichlorido, cobalt, ये this is like the name for this, and then you have chloride here. Okay, if I talk about now this K4FeCN6, then just name it. This will be named as potassium. Alright, potassium से start किया तो P capital, space छोड़ोगे cation और anion के बीच में, so potassium is your cation. Then you have hexacyanoferrate. It's incomplete without the coordination number. It's X minus 6 is equal to minus 4, because this is So X is equal to +2. +2 will be written as this हेक्सासाइनोफेरेट. अच्छा मान लो अगर यहाँ पे ये K4 नहीं होता तो इस पे एक चार्ज होता 4-, ठीक है. उस केस में आप पोटेशियम तो नहीं लिखते क्योंकि K4 है ही नहीं. सो आप इसको लिखते हैं हेक्सासाइनोफेरेट 3 स्पेस iron because now it is available in the ionic form. So then you have to name it as iron. There is only space between your cation and anion, and the coordination sphere, whatever you have in the coordination sphere, is written together. And in fact in your book now I found that even the first letter is at times not written as capital. So follow the protocol which is actually there. Okay, then I was talking about that there are sometimes compounds with some kind of a bridged kind of a complex also. If I have to talk about the bridged, then you have to, a Greek letter mu is attached before your bridging ligands. You may have some ligands which are forming a bridge. You may have some ligands which may be forming a bridge, like for example, I'm just looking at the example and just giving it to you. NH3O, you have cobalt, NH2, and then you have NO2, CO, and NH3 4 times, and NO3 4. If the generally you do not associate any sign with your oxidation state. Oxidation number is generally an oxidation number which in majority of the cases, or almost I think 99% of the cases, will be positive only. And just in case, because I don't say no to anything, just in case if you come across, just label the magnitude of the number in Roman numerals, right? Like where can you think of a negative oxidation state? Oxygen is like, if at all, if it is a central metal atom, which it is not. And generally you see that the central metal atom which is involved for coordination complexes are generally the ones which are electropositive in nature. They all are generally electropositive in nature and have a tendency to show variable oxidation states. Because D block की property ये होती है that they are small size, they have high charge density, and they have low lying vacant d orbitals, and then because of their low lying vacant d orbitals they can show variable oxidation states. Variable oxidation states matlab they can donate 1 electron, 2 electrons, 3 electrons, 5 electrons, 10 electrons, and so on. Cyano or cyanido? See, I think both are acceptable because earlier in some of the books you will find that even chlorido is written as chloro. But then I think what you can refer to is like cyanido. I'll confirm it with the examples that are generally given for your IIT JAM exams, and then just tell you cyanido because it's cyanide ion, so cyanido. Okay, so now here for the bridge ligands you generally use this Greek terminology before the names. Let's try and name this. See, in this you try and write what are the ligands. This is your ligand, this is your ligand, this is your ligand. These two are your bridged ligands. Ligand, ligand, bridged ligands. So here you have this is your NH4 thrice. 4 only. Let me just check out the example. NH3 4 times, NH3 4 times, and then you have NH3 4 times again here. Sorry for just copying it wrongly. This is a ligand, amine is a ligand here, nitrite tow is a ligand here, and amino is a ligand here. So when you start naming your bridge ligands, here you have an option, you can name your bridge ligands also even before the normal alphabetical order. But let's go according to the alphabetical order we've learnt. So it will be tetraamine. There are two ways of doing it. There are two metal ions now which are the same. Either you name it as dicobalt because you have to tell that this is a bridged structure. Ulta bhi to samajh mein aana chahiye na, that this is a bridged structure, so you can name it dicobalt, or you can name it stepwise. If you have to name it stepwise, then what is this? This is tetraamine cobalt. So you can actually name it like that. Tetraamine cobalt. Leave some space for its oxidation number. Tetraamine cobalt. And then hyphen mu. They've put it as amido. I think it should be amino. Mu amino. Mu nitro. Mu amino. Mu nitro. Because mu means they are bridged. And then again name the second half now. Mu amino. And what is the second half again? It's the same. Tetraamine cobalt. Tetraamine cobalt. And leave some space for the this thing. And what do you have outside? Nitrate. Simple nitrate, not tetranitrate, because this is the ionizable outside. So you leave one space here and write it as nitrate. Now you're supposed to work it out for this. This will be 4 plus. This will be minus and minus. So you will have 2x minus 2 is equal to minus 4. Can you work it out? You have to work out the oxidation number or the oxidation stage for your cobalt now. How many cobalt do you have? So 2x, alright, minus 1, ये दोनों तो 0 है charge. So minus 2 is equal to, what is the charge on the complex now? This is NO3 minus. So it is 4 minus. So the charge on the complex will be plus 4. So that is plus 4. So you have 2x minus 2x is equal to plus 6. So each x is equal to plus 3. So Roman number 3 here and Roman number 3 here. Clear? And there is another way of naming it also. That is, you name your bridged compounds first. You have mu amino, mu nitro, octaamine, dicobalt, 3 nitrate. This also can be a name which can be given. And there can be yet another name which is given to it. That can be mu amino, mu nitro. This also I need to tell you. Bis tetraamine cobalt 3 nitrate. All the names are correct. In this case, all the names are like correct. Nitrito is also correct. There are so many places where actually there is a dilemma between whether to use nitro or nitrito. You can actually write it as, here they are referring to it as nitro, and in many of the cases you will find it written as nitrito also, which is accepted. So it depends upon how you are actually naming and the options which are given in your choices. They will never confuse you for nitro and nitrito, because both of them are like acceptable, because NO2 minus is like a question which is nitrite ion. ठीक है, अब NO3 minus अगर होता तो it would have been nitrato, because that's nitrate ion. So that's like acceptable. Okay, now here, what did I state? That whenever you have a bridged ligand, then in case of bridged ligand, you can actually have, say, a mu attached before the bridging. So the moment you see a mu, that means there is some kind of a bridge which is getting formed. You understand the meaning of a bridge very well. So you can actually have, right, सबसे easy तरीका मैंने सबसे पहले किया है. The easiest way is that you start from one corner. What is that? You start with tetraamine. You know central atom is cobalt. Tetraamine cobalt. Roman numbers के लिए जगह छोड़ दो oxidation state के लिए. Then you have mu amino, And in some cases, when it is used, they write it as amido also. We'll just check up examples to find that out. Amino, then you have mu, nitro, then again tetraamine cobalt. Why do I write tetraamine first? Because remember, the central middle atom will never be named first. It will be your ligands which will be named first, but while listing them out in the formula, central atom is written. So it will be tetraamine cobalt, leave some space for the Roman numbers, and nitrate. That's the simplest way. Otherwise, you can name your bridged atoms first. It can be mu, amino, mu, nitro, then octaamine, because how many amines? Ligands to same hai, NH3. So it can be octaamine, dicobalt, and then the oxidation state for each one of them, nitrate. This is another way. And the third way that I have put is what? It is like you are naming your bridge ligands first, mu amino, mu nitro. Then you have in brackets, whenever there is a complex name of the compound, we generally use bis, tris, and tetrakis. Even if you have a ligand which is complicated, like PPH3, this is triphenyl phosphine. This can actually act as a ligand also. But for triphenyl phosphine, which already has a subscript, you actually can use a bis kiss or a tetra kiss, depending whether this is triphenyl, so one subscript is already associated. So if it is 2, it will be named as bis. And if it is 3 outside, it will name as Please explain the third naming. Yes, for the third naming only, I was explaining whenever you have a complicated name to be put in, you always associate with it with a prefix not as di, tri, tetra, and so on, penta and so on. Now here in this case, you generally name it as bis case, tetra case, and you won't be going beyond that. Tetra case means 4. So here in this case, you can actually then after putting the bridged ligands, you can talk about the rest of the system, because this is same and this is same, as bis, because this is double. Bis of what? Tetraamine cobalt 3. That's like bis because it is being repeated again. So one will understand ये तो bridge के हैं बीच के, and bis मतलब बाकी का जो भी हम name दे रखा है, whatever you write on the left hand side will be repeated on the right hand side. So it is mu amino, mu nitro, bis, tetraamine cobalt 3 in brackets nitrate. Nitrate is the simplest part. Alright, now having done some examples, very simple ones though, you can try out the examples which I have put on the screen here. Just try them out. Name the following complex ions. Name the following complex ions or coordination compounds. Don't put it on paper and then tell me. Quickly put it on paper. Don't rush through. Quickly. If there are around 15 examples that I've put here, you can see 10, 11 examples right here. I give you exactly say 2 minutes to solve the maximum. Let's see who gets the maximum number. Quickly. Page change करने का time waste. Yeah. Can we magnify it a little? First one I'll read it out for you is NiNH3 6 times and the charge on it is 2 plus. Alright. Can we discuss this? Tell me in chorus. सही होना चाहिए सबका. All of you all are brainy. It will be hexaamine. It's 2 plus. Why 8? What are you eating up now? There is no need for an 8. The 8 will be added to nickel only if it has a negative ion. So attractive बनाने की कोशिश नहीं करनी हमने. We have to name it as per the name. Now NiNH3 6 times will be hexaamine nickel put together. H can be capital or small. No problems with that. Hexaamine nickel in brackets 2. Because x minus x plus 0 is equal to plus 2. So x is equal to 2. So in Roman numbers 2, ion. Do you want me to write it on the board? Anybody, anywhere? So you have hexaamine nickel 2 ion. Next one AlF6 3 minus. आराम से आराम. Yes, now this has a negative charge. Hexafluorido. Fluoro both are generally acceptable. So hexafluoro aluminate negative 3 minus. Hexafluoro or fluorido both are acceptable. So hexafluorido aluminate and x minus 6 is equal to minus 3, so it will be plus 3 space iron. Don't write space, leave space. Next. Alright. No, I am giving say 5 seconds for each problem. Quickly write it down and then discuss. When I say go, then you start in chorus. मैं पढ़ देती हूँ. CuCN4 3 minus. Put it. Okay, time up. You have tetracyanocuprate. Copperate नहीं, cuprate. It's cuprous, which is cuprate, and then tell me the oxidation number for this. ये ऐसे workout नहीं होगा ना, थोड़ा सा हाथ चलाना पड़ेगा. Give your hand muscles some exercise. So this will be tetracyanocuprate 1 iron. Alright, 5 seconds for the next one. I'll give you time. Allow me to say start. Stop. Start. Triamine, tribromido. There is no number on it, so chromium. Oxidation number. Will you add iron to it? No. So this is triamine, tribromido or bromo, because your book teaches bromido, chlorido, but if general on a bigger scale, if you check out, it may be given as bromo also. So triamine, tribromido, chromium 3. There should be no doubts about it. X plus 0 minus 3 is equal to 0. So 3. Next one, start. FeOX3. OX means oxalate. So FeOX3 3 minus. Stop, start. Tris or tri, both are acceptable because some students find oxalate complicated, some find it simple. So tri and tris both are acceptable. Trioxalato ferrate x minus 6 is equal to minus 3. So it will be plus 3 iron. So trisoxalato ferrate 3 iron. Next, start. AgNH3 twice plus. There is a plus as a superscript outside the coordination sphere. AgNH3 twice plus. Did I say start? सबकी wait करो. We'll go together. Entrance में go ahead of everyone. This is AgNH3 twice plus. All right. Diamine, silver, 1 iron. Next, start. I'll read it out for you. FeH2O 6 times 3 plus. FeH2O 6 times 3 plus. Wait. Alright, stop. Hexa, aqua, iron, 3 iron. Hexa, aqua, iron, 3 iron. Done? Next. Jaldi likho. Be a little quick. Okay. CuCl4 with a 2 minus charge on the coordination sphere. I'm giving you time. And in 5 seconds you're supposed to stop. Stop. Tetrachlorido cuprate 2 iron. Alright, start for the next. PTEN twice 2 plus. PTEN twice 2 plus. Yes, yes, bis. Stop. Stop. Bis ethylene diamine. Bis and put ethylene diamine in brackets. After bis, trace, whatever, put it in brackets. So it will be whatever is generally put in brackets, it is prefixed with a bis case or a bis, trace or a tetra case. Alright. So it is bis ethylene diamine, platinum 2 iron. Yes. You can. You can. So there is a question, can we instead of, where is it? En. En is what? It is generally ethylene diamine, NH2, CH2, CH2, NH2. One of the students has just asked the question, can we name it as 1, 2 diamine? 1, 2. No, it will be 1, 2 ethane diamine or ethane 1, 2 diamine. The entire nomenclatural name should be there then in brackets, right? So you have to take care of that. Alright. Are you all able to cope up? Naming is very easy, interesting, scoring, and is always asked in the examination also. In any type of an exam that you go for. So it is very important for you to understand it pretty well. We are just starting with simple examples and we'll take more complicated examples in the next class. So here what we have is PTEN twice 2 plus done. This is like bis, put in brackets ethylene diamine, platinum 2 in Roman numerals. Okay? Put the name of the IUPAC name of ethylene diamine in brackets and put a bis outside. It would be 1, 2 ethane diamine because ethane है CH2 is ethane और 1 or 2 पे amine लगा हुआ है तो it will be 1, 2 ethane diamine, that will be in brackets. So bis 1, 2 ethane diamine, platinum 2 iron, or bis ethylene diamine, platinum 2 iron. Both are correct because your naming should be right. Then for the next one, CO NH3 4 times NO2 Cl, and outside the bracket you have a plus. Alright. I gave you enough time because we solved it out also. This will be chorus, go in coordination. 1, 2, 3, start. Alright. Tetraamine, chlorido, very good. Nitro, cobalt. Find out. It will be X minus 1 minus 1. So that means minus 2 is equal to plus 1. So it will be 3. Which one did we solve? The CO's NH3 4 times NO2 Cl, right? So the name is, I repeat, tetraamine chlorido nitrito cobalt 3 iron. Nitro and in some cases chloro is also acceptable because when you check out more assignments on web, you will find that there are terminologies which vary. But I suggest that you follow what is given in NCERT in your text, CBSE texts. Okay? Now we are on the kth problem. CO NH3 5 times Br SO4. Br till Br it is in coordination sphere. Then you have SO4 outside. So please name it. This will be 1, 2, 3 start. Pentaamine bromido cobalt sulfate. 3 sulfate. Alright. Pentaamine bromido cobalt 3 sulfate. Done? Done? Move on to the next question quickly then. Quickly. Alright, next. We have here CR. Now here we have a double coordination sphere, right? Can you just lift it a bit? Now here the mth problem, this is done, no? We are on this problem now. For 1L is left. Do it quickly. CO, NH3 5 times, SO4 and Br is outside the coordination sphere. So you have pentaamine sulfato. You have pentaamine sulfato cobalt 3 bromide. This is similar to the previous case, so no problems. You have pentaamine sulfato cobalt 3 bromide. 3 is in Roman numerals within brackets just after your central metal atom. It is representing the oxidation state. Just to remind you, you will be leaving space after the coordination sphere is named and name your anion as bromide. Now in the next case, that is 1M, the problem that I have put on the screen is like CrNH3 6 times. That's a coordination sphere that acts as the cation, obviously, because you always write cation on the left hand side and the right hand side will be your anion. So COCN6 and this will be again this will be negative. So one thing is clear, that you name your ligands here. It is hexaamine chromium, which is very simple. Leave some space in the bracket for the oxidation number, and then you have hexacyanido or hexacyano cobaltate with, why? Because the first coordination sphere, ये general चीजें हैं. First coordination sphere will be positive only and the second coordination sphere will be negative. So here you have a double coordination sphere. So you have the name for the first one is very simple, hexaamine chromium, brackets में खाली अभी छोड़ दो. We'll talk about the oxidation state. Space. Now name the anion. The anion will be hexacyanido cobaltate because it is negative, you know that. And in brackets, just leave for the oxidation state. Now, from your knowledge till now, what is the general oxidation state for cobalt in all these? It is +3. ठीक है? तो let us assume कि इसमें भी +3 है. ठीक है? ध्यान से सुनना and इसको समझ लो. Because the only task here is to assign an oxidation state to both the metal atoms. One in the one coordination sphere of cation and the other coordination sphere which is like a negatively charged. So if cobalt is 3, so this is +3 minus 6. What is +3 minus 6? +3 minus 6 minus 3. So a charge of -3 comes on top of the coordination sphere. If -3 has come here, then that means this has +3. Then chromium will have a charge of, which is also possible. So 3 and 3 both are acceptable here in this case. So you will have hexaamine chromium 3 and hexacyanido cobaltate 3. For cobalt generally it is +3 only. You will not be taking common, but you will be working it out, because in some cases had it been iron here it would have been +2 also for all you know. But you know that for iron +2 +3 both are possible. This knowledge you will get when we will do D and F block, because the number of oxidation states for D block elements are variable. So they can exhibit different oxidation state, and that is again a plus point here. That they had it been iron it could have been +2 or +3, both were acceptable here. So you have to say, if you now take it to be say +2, cobalt can also be as COCl2. Say if I take CO as +2, now the doubt is, let's take some other oxidation state. If I take +2 here, +2 means +2 minus 6, +2 minus 6 will be -4. So then this becomes +4. So chromium in +4 is not stable, so you do not accept that. So the best possibility is, जितना ज़्यादा इसको practice करोगे उतना you will get the hang of how to name it quickly. But don't be in a hurry, because ये सबसे scoring question है जिसमें there is no मतलब you should not be having a doubt in the answer, and it should not go wrong also. It is that simple. So you just have to devote about 3 to 4 seconds time and you will be able to solve this question, so that you give more times to the other sections and other parts. So next, hexaamine chromium 3 now, and space chromium 3 space hexacyanido cobaltate 3. Now for the next, you have Na3 outside the coordination sphere. Then in the coordination sphere you have CO, NO2, please excuse me, this 2 is a subscript, CONO2, 6 outside nitro, and then you have this. So the name will be sodium space hexa nitro cobaltate 3 nitrite. Sodium hexanitrite cobaltate 3. Alright, next, the last one, nitro. But I still suggest please go back to your text and find out, because what I have seen is that in your text chloride is given as chlorido only, bromide is given as bromido only, nitrite is given as nitrito only, so you refer to nitrito only. The text that I have actually picked up will be talking about the other cases also, like here. We'll just move to this question in a short while. Here you have tetrachlorodiamine, nickelate and so on. So this chloro is nothing but your chlorido. So you should be like kind of open to all these, but for your normal text you have it as chlorido, nitrito, so refer to that only. So please, I apologize if there is any discrepancy. So nitrito, cyanido, chlorido, this you all understood, just an O. So that O has to be attached. For the last problem, quickly, you have COEN tri-Cl3 outside the. Stop, since it's the last problem, we'll go together. Bis, ethylene, tris, ethylene diamine, cobalt, 3 in brackets, space, chloride. That's it, alright. So you all can name it pretty well. We've talked about the Brit structure also. So we can then move on to say the naming, writing the formula, because now it can be the other way around also. You may be given the name and you have to write down the formula. Now I tell you, it is going to be a cakewalk for you. Why? Because if you know how to name it, then writing back the formula should not be a difficult task at all. And we'll quickly go through it. Alright, for formula writing, remember, if I am talking about the formula writing, the central atom is always listed first. For writing the formula, the central atom is always listed first. So if you're, say now it is like just a reverse care of what we've done just now. You are given the name. ब्रैकेट्स में लिखते टाइम हम सबसे पहले क्या लिखते हैं? We'll be writing cations of course पहले. I'm just generally putting the points here. We'll be writing cations first, and central metal atom will be listed first. So it should be given the first priority to write down the central metal atom. Otherwise name करते टाइम हम सबसे last में उसको name करते हैं, but लिखते टाइम सबसे पहले we'll put down the central metal atom. Then the ligands are placed according to the alphabetical order. वो तो नाम में भी alphabetically ही होंगे. So formula write करते टाइम भी you can actually check it out that while writing the formula also they are generally put in the alphabetical order. Or if it is not, you should understand that even if Cl is written before Br in the formula, you know that while naming it gets corrected. Because naming में आप alphabetical order follow करोगे, क्योंकि it will be bromido then chlorido. So that order is followed. It is a better thing that while formula writing you should write Br first and Cl later. So it is like ligands should be placed according to the alphabetical order. Even the polydentate ligands. Polydentate कौन से हैं? Name the polydentate ligands please. EDTA बस, और कोई डाइडेंटेट बता दो फिर. Ethylene diamine, ठीक है. And then remember that the coordination compound should always be listed in a square bracket. Formula लिखोगे तो सबसे पहले it's saying that when you write down the formula you should be numbering your metal first. Then you should go with your ligands in alphabetical order. Say ligand number A first, followed by B. All these ligands should also be put in parentheses. इन ब्रैकेट्स, ये सिंपल वाले ब्रैकेट्स A B C D, फिर अपने लिगेंड्स का अल्फाबेटिकल ऑर्डर लिख लेना जितने भी. Once you are done with that and tri tetra will be put as a subscript. ये सब चीज़ें मतलब आप देख चुके हो, ठीक है. And then that has to be put in the coordination sphere, and then there will be a little space between metals and ligands. You will of course not be sticking them together. Charge is indicated outside. Remember that you have to indicate the charge, or if the charge is not there, you will be naming the counter ion. You will be putting the counter, not naming, you will be putting the counter ion there. And counter ion will also be according to charge. क्योंकि अगर 3+ चार्ज है और बाहर सिर्फ क्लोराइड लिखा है तो आप Cl नहीं लिख सकते. You will have to write Cl3. Did you get the point? That for example, if you have a metal with a 3+ charge, chloride, space chloride, that is how you've been naming it. So chloride से तो कोई indication नहीं है कि Cl में क्या नीचे subscript है, लेकिन it is understood from the chemistry that you've learned till date that if you have a charge of 3+, तो कितने Cl आएंगे फिर बाहर? 3. So remove the charge and write down the counter ions properly. So counter ion should also be put properly according to charge. So understand? And charge is always balanced by the counter ion. This was the last point. It is always balanced by the counter ion. Got it? I repeat it. Now we are just going the reverse way. If you are given the name, you are supposed to write down the formula. If we are writing down the formula, central atom should be placed first. We start listed first. After listing the central atom, it is followed by ligands, generally put in the alphabetical order. And once they are put in the alphabetical order, then we any kind of ligands follow the alphabetical order. Then we enclose your coordination complex into the square brackets. After that, we either put the charge if it is an ion on top of it. Charge कैसे पता चलेगा? If you have the oxidation state with you, that oxidation state plus the oxidation state of the anions or ligands that you have, that will be totaling up to the total charge on your complex. I repeat, charge कैसे पता चलेगा coordination sphere का? जो भी charge है on your central metal atom, which is generally listed in the brackets Roman numerals में, उस charge को plus the charge on your ligands will be the total charge on your coordination complex. अगर वो charge नहीं दे रखा and you are given a counter ion, then that charge has to be balanced by your counter ion, the oppositely charged ion. Okay, let's take up one example. I will just take one example from here and then we'll move to the questions that I put on the screen. They say the first, write down, there's no harm in noting it down also. You have the first one as tetraamine, aqua, chlorido, cobalt, 3 chloride. So cobalt सबसे पहले, ठीक है, start with your coordination sphere. cobalt सबसे पहले, tetraamine, this is like very quick, tetraamine, aqua is simply water, chlorido is simply Cl. Alright, done. Square bracket closed because हमारा coordination sphere खत्म. Then you have this is +3 +0 +0 -1. What is the charge? +2. ठीक है? Cobalt is in +3 oxidation state. +0 +0 -1. तो charge क्या हुआ coordination sphere पे? It will be +2. And then you have chloride. So it has to be balanced with chloride. So I remove this +2 and I write Cl2. थोड़ा पास ले जाऊँ because they have not fought with each other. Cl2. ठीक है? Now you try the next that I put on the board. It's an easy one. Potassium, tetrahydroxido, alright, zincate 2. Quickly. potassium tetrahydroxidozincate. What will it be? K first potassium. अभी तो नहीं पता ना कि K को कैसे बैलेंस करेंगे, so इसीलिए उसके बाद coordination sphere start हो गया है, so it would be Zn OH tetra है तो 4 coordination खत्म. It will be a minus charge on the complex, this is for sure. This is plus 2 minus 4, so the charge is minus 2. This minus 2 will be balanced with K2. K2 is the name of a peak also. Anyways, we are doing chemistry, so it's potassium tetrahydroxidozincate. Now, I think you should do only the first 5 problems that are given here. If we can just pick it up a little. Write the formulas for writing dicyanoargentate 1. अब इन सब के 5 के फॉर्मूले लिख लो, so that we move, और 4 के लिख लो पहले quickly, and then we move on to the next part, that is isomerism. Because of paucity of time, we need to move ahead. So you practice those and quickly. I am giving you exactly 2 minutes to solve the first 4 formula. Not even 2 minutes. You should be given 1 minute for that. I'll put down the correct answers on the board. The first one is dicyanoargentate 1 ion. So that is AgCN twice minus. It's an ion, alright. The second one is NiNH3, very good, twice Cl4, and you have 2 minus. Right, next you have PtCl6, 2 minus. And the fourth one is Na2CuCl4. Look into your partner's notebook if they could do it correctly. Look into your partner's notebook. If they could do it correctly, put a wrong wherever it is wrong, and then because you've done it quickly, I think you can take up the next examples also. Yes, try it out quickly. You have potassium hexacyanoferrate, bis, ethylene, diamine, copper 2 ion quickly, and I think you can do the rest also till J. Do it till J quickly. The first one is very simple. K4, very good. K4 FeCN6. Look into your partner's notebook if that person has done it correctly. Not to copy but to check. Okay. Then the next one, Cu. What is it? F1. Cu. En twice. 2 plus. EF. And now G. H, I, J. Done? Done? All? I'm giving you another half a minute. Quickly do it. Fifteen seconds left. Stop. 5 seconds gone above. G part. Tell me. In square brackets, Al, H2O 4 times, OH twice, Cl. Alright. Keep a check of your partner also. Because if you help the partner, I think it will give you extra credits in the final examination. So then you have Al, H2O 4 times, OH twice, and Cl. Fine. Then the next one is which part? H part? Alright, Cr, En twice, tell me. NH3, Cl and SO4. Absolutely right. Alright, next I part? Yes. Yes. Not complete, tell me ahead. NH3, 4, which one is that? That is I. What? तो ये भी तो बताना पड़ेगा ना, मैंने ही तो गलत लिख देती. Here aqua and ethylene diamine, this should be coming first. All right, next J part. No, sodium, Na3, AlF6. Please mark yourself on your own based on this, because if you can do this, then the rest of the chapter is going to be easy for you. करना अल्फाबेटिकली चाहिए. ये अमीन, ये एक्वा है तो अमीन को पहले डाल दो. Cr NH3 4. No, but then the way it has been put here must be the same only, no? Triamine, what is this? I part, no? So tetramine, so it should be NH3 4 times H2O twice. And as it is, I told you, generally formula writing is like you go accordingly systematically. But for naming, you have to be absolutely particular that that should be put alphabetically. Here sometimes you may find that they may be haphazard. तभी तो naming करते time आपको ध्यान रखना पड़ता है कि which one is alphabetically first. Okay. Then I think now we move on to one of the most important parts, that is isomerism. Done with this? Take a deep breath till I rub the board. Taken? Alright, next we move on to isomerism. You know, isomers are what? Change of topic now, a little. Yes, the ones which have the same chemical formula but different structural formula. Achha, now there are two types of isomers that we generally talk of in terms of coordination compounds. One is the stereoisomers, and then you have structural isomerism. Alright, now in case of stereoisomers, let me tell you, they have the same chemical formula and different structural formula. That is there in all. They only change in spatial arrangement, but the number of the chemical bonds remain intact. In stereoisomers case, what you have is they differ. They have the same chemical formula in the bonds, but in case of structural, there is a change of or shifting of the bonds also. In this case, when you put it on paper. Now for stereoisomers, you have two types. You can have geometrical isomers or you can have optical isomers. Alright? And in structural, first you know the types and then we'll go ahead. In structural, you can have linkage isomerism, you have coordination isomerism, you have ionization isomerism, and you have solvate isomerism. ये coordination compound है ना, इसलिए ये थोड़ा सा different है. Alright, I repeat. In case of structural isomers में there is a change of bonds. But here the chemical formula as well as the bonds remain the same. In case of this is only caused generally by the rotation. Now here for the structural we are talking about the linkage isomerism, ionization isomerism, coordination and solvate. पहले तो चारों types learn कर लो. पहले main type है structural and stereo. Stereo में it generally refers to keeping the let's talk about it. In this involves the breaking of the bonds and new formation of the new bonds. Structural में, ठीक है? What are the four structural isomers? Tell me without looking onto the board. Linkage, coordination, ionization, and solvate. Repeat it again. Linkage, coordination, ionization, and solvate. One last time. Now, what changes in ionization isomerism is that the ions change. जैसे नाम suggest कर रहा है, you basically have a shift of ions. I'll keep putting the examples and keep rubbing them because what I want you to remember is this broad classification. Because किसी भी अगर formula का you are supposed to calculate the isomers, then there are different types of isomers which are possible. जिसका ionization isomer possible है, हो सकता है उसका एक stereo isomer भी बन रहा हो. So you do not have to forget about that. And what are the two types of stereoisomers? You have geometrical and optical. We'll talk about that. In optical, you generally have D and L. डेक्स्ट्रोरोटेटरी एंड लीवोरोटेटरी, एंड हियर फॉर ज्योमेट्रिकल जो आपने अभी तक पढ़ा है सिस एंड ट्रांस, ठीक है, ये पढ़ा है अभी तक. लेट्स सी व्हाट more has to get added on. Now I am throwing light on the ionization isomerism first. All right, in ionization isomerism, just look up onto the board, no need to write anything. I want all of you all to pay attention to the board. COCl2 NH3 4 times NO2. All right, now you know one thing from the knowledge of coordination compounds, that the secondary valence will remain intact. The number of ligands cobalt के पास अगर 4 है इस केस में, so those 4 will remain the same. So here you have COCl2 NH3 4 times NO2. What is the ion which will get formed? Plus of this and minus of NO2. If I take this NO2 inside and Cl outside, then the ions will change. Chemical formula remains the same. So then in that case it will become CO, Cl, NO2, I could have written NO2 after amine also, NH3 4 times, and you have Cl outside. So what has happened? The ions have changed. So ions got exchanged by the outside and the inside of the sphere. समझ में आया? Ionization isomer, so these two. So if you're given one compound, then how many ionization isomers are possible can be listed using that. Only one. isomer one of this, क्योंकि इसके अंदर सिर्फ एक ही exchange possible है Cl. Ammonia will not come outside. Why? Because that will alter the, that's neutral. So if you're giving one charge inside, then it can, so the ions are different now. So this is called as ionization isomerism. Clear with ionization isomerism? Basically it is the one in which the compounds have same molecular formula but gives different ions on dissolution. So then it depends on whether it can take up that oxidation state or not. You will have change of solvent also, that is known as solvate. अगर ammonia ही बाहर आ जाएगा, then it will contribute to another type of isomerism which is solvate isomerism. ठीक है, ध्यान इधर. You have structural isomers of 4 types, out of which I talked of ionization isomerism. इसमें क्या है कि coordination sphere के बाहर ion exchange हो गया, NO2 गया अंदर, Cl आया बाहर. So now you have change of ions on dissolution, so you call them ionization isomers. Alright, next we talk about say hydrate or solvate isomerism, in which say the water of crystallizations that we have, they change. So what we have here is, say for hydrate isomerism you have Cr, Cl, H2O 5 times, and you have Cl here, H2O. So what can happen in this case? The coordination number has to remain the same. The coordination number has to remain now 6 for Cr. So what can happen? I can change the number of water of crystallizations outside. I can put one Cl inside and take one H2O outside. That will change it as Cr, H2O 4, Cl2 हो गया. You can just put 2 here also. It becomes for Cl because it's simple 2. This becomes dot 2H2O. So what is changing? Wherever it is possible to change or exchange your solvent molecules also, there you call it solvate isomerism. Alright, where there is a possibility, but remember that the secondary valence will always have to be maintained a constant. Charge will get balanced depending upon the oxidation states which are allowed. So no need to pay attention to a great extent to that, because generally the water of crystallizations lie there only wherever it is a possibility to exchange. So you have Cr, Cl2, H2O 4 times and dot 2H2 here. Here you had only one water of crystallization. Here now you have 2 water molecules. No, it can be used for other solvent molecules also, like sometimes you use ammonia as a solvent. So that is why if you are using it for case of water, what do you call it? Hydrate isomerism. Otherwise generally for any other solvent it will be solvate isomerism. No, yeah, because solvent is generally neutral. You do not have any charged solvent. You generally don't talk of any charged solvent in case of coordination complexes, at least at this stage. So ionization done, then solvate or hydrate done. Let's talk about coordination isomerism. Now see, coordination isomerism is possible where you have two coordination spheres. ठीक है, ये याद रखना कि coordination isomerism बोलते हैं you should have two coordination spheres. That means the cation should also be a coordination sphere and an ion should also be a coordination sphere where the exchange of ions is possible, like CO, NH3 6 times, and you have Cr, NH3. Alright, because we want to change it, CN6. Alright. So what can happen here in this case? Cr can come here and CO can come here. So then in that case you say that the coordination sphere in fact has changed for the metal atom, and because the coordination sphere for the metal atom has changed, you call it coordination isomerism. This is always possible whenever you have double coordination spheres. हाँ, या फिर अगर मान लो यहाँ पे 4 है और यहाँ पे 6 है, तो भी ये पॉसिबल होना चाहिए कि that should also be compatible with the same oxidation states. वो भी केसेस आएंगे मे बी क्वेश्चंस करते टाइम. आई लुक फॉर एन एग्जांपल where you have say 4 ligands here and 6 ligands here, still your cations are capable of exchanging. That also is a possibility. So what will be the coordination isomer for this? It will be Cr NH3 6 and you have CO changing its coordination sphere as CO CN6. Alright, now there is a change in coordination. So this is what is your coordination isomerism. Ligands भी shift कर सकते हो. So अगर ligands shift करोगे तो उस केस में भी you will call it a coordination isomerism only. But then in that case it is like one and the same thing, because जब आप ligands shift करते हो तो उसके charges change होंगे. Charge change होगा तो फिर वो negative हो जाएगा तो फिर वो इधर आ जाएगा. So it is all done on the basis of that study. हाँ, तो फिर वो सारा गड़बड़ जाएगा. तो वो देखना नहीं that is all. See, इसमें क्या करा, अगर आप कह रहे हो इसने कोऑर्डिनेशन स्फीयर बदला तो लिगेंड्स तो ऑटोमेटिकली बदल गए. समझ रहे हो मेरी बात? अगर हम CO is in +3 oxidation state here and it is in +3 oxidation state here also. Her question is very valid. आप मैंने क्या करा, मैंने मेटल्स उठा के इधर उधर कर दिए. जब मैंने मेटल्स उठा के इधर उधर कर दिए, when I just shifted the metals here, she asked me a question if I can shift the ligands also. I said ligands shift करोगे तो चार्ज चेंज होगा. चार्ज चेंज होगा तो ऑटोमेटिकली अनायन को उठा के आप राइट में ले आओगे. अब क्या है, अगर इसको +3 और इसको भी +3 मान रहे हो तो here if it is +3 and then the total charge on this is +3 because ammonia is neutral and इसका चार्ज कितना है +3, so it becomes -3 on the coordination sphere. +3 -6 so it is -3. अब क्या है कि अगर मैं लिगेंड्स चेंज कर रही हूँ, मान लो CN को इधर ले आई, अमोनिया को इधर ले आई, यही चीज करिए. अब CN को इधर लाएंगे तो दिस इज +3 -6 इट बिकम्स -3. तो ऑटोमेटिकली मुझे उसे उठा के अनायंस वाली साइड पे लाना पड़ेगा. जैसा क्वेश्चन था वैसे ही आंसर किया मैंने. दोनों वैलिड है. So that means your coordination sphere के अंदर का material is changing without altering the stability of the coordination sphere. It should be stable. Configurational isomerism is the one in which your configuration is changing. See, when you talk about configurational change, you are talking about basically a change in the structure altogether. So that is what is your configurational isomerism. That is what it refers to. Okay, that's like a broad classification only. The isomerism in which your configuration is changing, and the configuration is changing when you are actually changing the structural formula and keeping the chemical formula the same. Okay, next what we have is I have taken example. So ionization बोलते ही क्या याद आएगा कि हमें आयन उठा के एक्सचेंज करने हैं अंदर और बाहर कोऑर्डिनेशन स्फीयर के. वो Cl को NO2 से रिप्लेस कराओ या Cl को दो Cl को SO4 2- से रिप्लेस कराओ, दैट्स योर चॉइस. सो जहाँ पे दो आयन्स हैं, एक बाहर आयन है और एक अंदर आयन है, उनके बीच में एक्सचेंज पॉसिबल है. सो देन यू विल गेट आयनाइजेशन आइसोमेरिज्म. सॉल्वेट तब पॉसिबल है जब आपके पास डॉट कोई सॉल्वेंट मॉलिक्यूल हो. अंदर हो या बाहर हो, अगर बाहर भी, जैसे हमने वो वाला केस किया था COCl3 व्हाट इज दैट .6NH3, यही था ना केस. सो अगर इस केस में आई हैव CONH3, नाउ पे अटेंशन टू दिस केस ओनली, CONH3 Cl3, ठीक है, ये वाला एक नॉर्मल स्फीयर था. हमने बाद में क्या करा, CONH3 it became 5 Cl inside and Cl2 outside dot, so वो ये क्या हो गया, अचानक ध्यान आ गया, ठीक है. सो सॉल्वेंट में जहां पे भी ये सॉल्वेंट का, अब ये और भी हो सकता है, यू कैन हैव CONH3 4 times Cl2 Cl outside dot, this is another possibility. So इसके number of solvate isomers बढ़ते जा रहे हैं depending upon what is the possibility of the exchange. तो जब solvent molecules change हो जाएं outside, then it is known as the solvate. If this solvent is water, you call it hydrate isomerism. That's like one and the same thing, you can call them anything. Then for coordination isomerism, it is very important that you have at least 2 coordination spheres where the exchange of ions or the exchange of the metal atoms basically, उसको easy है to understand. metal इधर का उधर shift हो जाए और उधर वाला इधर shift हो जाए, तो then in that case you call it the coordination. basically क्या है कि coordination sphere की property ही change हो जाएगी. अगर central metal atom change हो गया, as I used a phrase before, one king for one palace, अगर वो king अपना palace ही change कर देगा तो फिर वो जो king की rules and regulations हैं वो फिर दूसरे palace पे लगेंगे. Getting the point? So that's like a very weird example which could not bring smiles to your faces. I am disappointed. So here, okay, now we move on to the next type, which is linkage isomerism. Linkage is very simple for you to understand, because all of you all understand ambident nucleophiles, ambident ligands, sorry, here I should be calling them ligands here. So if I have CO, NO2, NH3, 5, Cl2, then what is the ambident nucleophile here? NO2 minus. So this can also be written as CO, ONO, NH3, 5, Cl2. Remember, in this case ionization isomerism is also possible, पर मैं अभी सिर्फ जो समझा रही हूँ वही बता रही हूँ. लिंकेज आइसोमेरिज्म मतलब अभी ये लिंक्ड है N से, अब ये लिंक्ड है O से, लिंकेज चेंज हो गया, इट रिमेन्ड एज नाइट्राइटो, दोनों केसेस में नाइट्राइटो है, लेकिन दिस इज, तो इसीलिए कई बार इसको नाम देते टाइम हम लिख देते हैं दिस विल बी पेंटाअमीन डैश कैपिटल N डैश नाइट्राइटो, ये बताने के लिए जो नाइट्राइटो का पॉइंट ऑफ अटैचमेंट है दैट इज कैपिटल N. और इसको कैसे लिखोगे, पेंटाअमीन O हाइफन O कैपिटल O हाइफन नाइट्राइटो cobalt and then the rest of the name, correct? So this is your linkage isomerism. So all the 4 isomerisms done. Linkage isomerism. So linkage is the one in which you have ambident ligand. ambident ligand देखते ही linkage दिमाग में आना चाहिए. 2 coordination sphere देखते ही coordination isomerism. 2 ions, जो अभी मैंने example लिखा था उसमें 2 ions भी exchange हो सकते थे. NO2 could have got exchanged with Cl outside. Cl था बाहर, अंदर NO2 था, तो that is a possibility of ionization isomerism. और जहाँ पे भी you have solvent molecules attached to your system, then you can also have solvate isomerism. Now we are moving on to the next type, which is stereoisomerism. In case of stereoisomerism, now you have 2, geometrical and optical. What are the 2? Geometrical and optical. Now geometrical isomerism occurs due to ligands occupying different positions. Geometrical में you have ligands occupying different positions. You already have cis and say trans. Alright, cis is like when the ligands are on the same side, trans is when the ligands are on the opposite side. Let me just explain it with M, A, B, 2, lest I give you wrong examples. Here you have M एंड ये किस में पॉसिबल है, जहाँ पे लिगेंड्स मेरे A2 और B2 टाइप में हो, दो एक टाइप के, दो एक टाइप के. It's possible there. If the shape is square planar, then you have MAA and you have BB. तो ये क्या है, because they are on the same side, so it is cis. Alright. If I put 1B here and I put A, so they are opposite to each other, then it is trans. Alright. This is also possible in case of MA3B3 केस. जैसे MA2B2 ये तो स्क्वायर प्लेनर सा लग रहा है ना, इट्स काइंड ऑफ अ स्क्वायर प्लेनर structure. When I talk about an octahedral structure also, there also I can talk about cis and trans. Let me just put it as how. Say when I talk about the octahedral complexes, then say if I have MA3B3 types. Octahedral कैसे होता है? You have central metal atom here. This is your metal. चार प्लेन ऑफ द बोर्ड पे, जैसे ये मेटल अगर मैंने प्लेन ऑफ द बोर्ड पे रखा है तो चार जो लिगेंड्स होंगे वो प्लेन ऑफ द बोर्ड पे होंगे, एक ऊपर और एक नीचे. सो इस केस में अगर A ये आर टुगेदर एंड यू हैव B and then these are together, then you actually are calling them kind of a cis. This is kind of a cis, and there is another naming for them, that is facial and meridional. You have FAC and MER isomers also, which are generally given. I'll just put it for you. You try and draw the other isomer for this. Try and draw the other isomer. So in this case, I'm just looking up for an example. I'll just put it for you. If three are on the same side, then you call them facial. This is like the FAC isomer, facial isomer. Alright? And if you have them on an opposite side such that you have A here and you have another A here, B and B. Then in that case, see, when they are together absolutely, you call them FAC. When you are separating them out now, when you are separating such that coordination में एक triangle ऐसे नहीं बनेगा, you have a B coming in between, then you call it MER isomer. MER, MER, that stands for meridional isomer. And the example for this type is you can have CONH3 thrice, which is given in NCERT, and NO2 thrice. When all the three A's, this will form an octahedral complex. ठीक है? Octahedral आप सबको पता है, all the angles are 90 degrees. So four bonds are on the plane of the table, one bond is above and the one bond is below the plane of the table. So if your A's are all together such that they can see each other just on an adjacent manner, then that is known as a facial isomer. When they are separated by just one atom in between, another bond comes in between, then it is called as meridional or MER isomer. Got it? But if you have say an example like, I'll take up an example, COCl2En2. ये समझ में आ गया सबको? देखो, square planar is easier to understand. When I talk about square planar, the example that is generally given for a square planar, cis and trans is PT NH3 twice and Cl2. जब दोनों NH3 square planar मतलब everything is on the plane of the table only. So PT is at the center. You have PT here, NH3 एक बार इधर. So this is your cis, and when I just place one Cl opposite to the other Cl and NH3 opposite to NH3, then it becomes trans. So you understand that cis and trans very well. So whenever you have a tetra coordinated metal atom, टेट्रा कोऑर्डिनेटेड मेटल एटम जहाँ पे 2 और 2 का ऐसे डिमार्केशन है. देन यू कैन हैव सिस एंड स्क्वायर प्लेनर स्ट्रक्चर हो सकता है. ज्योमेट्री कैन ऑल्सो बी tetrahedral, but tetrahedral में it will not show you stereoisomerism because all of them are considered to be equal locations. लेकिन square planar में if they are like either on the same side or on the opposite side, because then the angle changes to 180. tetrahedral में क्यों नहीं बोलते हम इस, why are we not talking in case of cynido? The answer to the question that just came up, cyno and cynido, you can write it as cynido. All right, then you have here PT NH3 twice Cl2 can show you geometrical isomers which can be cis or trans. सेम से ये तो बहुत कॉमन है और आपने पहले भी पढ़ा है, सेम साइड वाले cis, ऑपोजिट साइड वाले ट्रांस. Another example for this which is given in a very nice fashion is you can have CO En twice Cl2. This is cobalt ethylene diamine. This is also named as cis and trans because CO में अगर आपने से Cl और Cl अगर वो दोनों एक दूसरे के साथ ऐसे हैं तो यू नो दैट द अदर पोजीशंस ये बचती हैं और 4 पोजीशंस. अगर CO इज हेक्सा कोऑर्डिनेटेड, आपको पता है En में कितनी साइड्स हैं, वो 2 पॉइंट ऑफ अटैचमेंट देगा. इथिलीन डायमीन तो हर एक 2 जगह से कंट्रीब्यूट करेगा En, तो कितने पॉइंट से अटैच करेगा ये 4. सो 4 पोजीशंस हियर एंड यू हैव Cl2. ठीक है, तो इस केस में अगर ये दोनों Cl साथ में हैं एंड यू हैव En हियर एंड En, डू यू वांट मी टू राइट इट लाइक दैट? NH2, इट कैन बी रिटन एज CH2 CH2 एंड यू हैव NH2. ठीक है, इसको En भी लिख सकते थे सिंपल. तो अगर ये दोनों साथ में है तो ये सिस है. और अगर मैं एक Cl को उठा के चेंज कर दूं, इफ आई जस्ट चेंज वन Cl, if I place Cl on the top and Cl in the bottom, this is the only possibility with En. Cl on the top and Cl at the bottom. तो फिर मेरा स्क्वायर प्लेनर के केस में En आ जाएगा इधर. सो ये दोनों जो हैं, तो आपने CO रखा टेबल पे, En और En भी रखा टेबल पे, तो वो स्क्वायर प्लेनर टाइप ऑफ स्ट्रक्चर दैट विल फॉर्म क्लोज स्ट्रक्चर. Cl on the top and Cl at the bottom. This is your trans. समझ में आया? Say a bigger yes. So this will be your trans. And अगर वो दोनों can see each other very comfortably and shake hands, so then it is cis. Although this is an octahedral. Otherwise हम octahedral में किस चीज़ की बात करते हैं? Fac and mer. That is Ma3B3 types. ठीक है, ये सारे जो हैं ये हमारे these are the types of geometrical isomerisms. Displaying geometrical isomerism. All right, next is a very important one, that is your stereo or optical isomerisms. Remember that optical की speciality क्या होती है? Optical सिर्फ वही वाले elements show करेंगे, वही वाले compounds optical isomerism show करेंगे which form non-superimposable mirror images. That means इसको बहुत clearly समझ लो because ये organic में भी बहुत details में करोगे. When you are talking about optical isomerism, then that means if I see this hand, तो इसका mirror image will come something like this. If I talk about this hand, all right, then the mirror image will be like this. Imagine करो ये mirror है और ये इसका mirror image है, ठीक है? So you will feel that ये तो superimposable हो गया, ये तो superimpose हो गया. लेकिन ऐसे नहीं superimpose करना. Superimpose पता है कैसे करना है? ये है the main molecule and this is the mirror image of the molecule. You will just simply lift it up and now place it on top. Now is this superimposable? No. So that means it is displaying optical isomerism. Your one important essential criteria that you all can write down is that your optical isomerism will only be shown by that compound which forms, will only be shown by that compound which shows a non-superimposable, मतलब वो superimpose नहीं होनी चाहिए, same नहीं होनी चाहिए, non-superimposable mirror image. ठीक है? Clear with this? And mirror image का मतलब ये नहीं है you will just rotate it and put it like that. No. 180 degree rotation will always give you the same molecule. अगर मैं mirror image को 180 डिग्री से रोटेट करूंगी फिर वो मेरे को सेम दे देगा. image. Now if this is the main molecule, I will look into the mirror image and then just lift it and put it on top. ठीक है, rotate करूँगी 180 से तो I will get the same. So I don't have to rotate because rotation by 180 degree generally gives the same molecule in case of optical isomers. 180 degree के rotation से याद रखना कि same molecule वापस आ जाता है. So this is the mirror image. I will pick it up and put it on top of it. This forms non-superimposable images, which means that the structures are chiral. CHIRAL. So such structures are called as chiral and they display non-superimposability or will show optical isomers. So I will just give you an example of this. For say optical isomers, I will look into the text only. Say if I have COEN thrice. Now you try and place it in the octahedral form on your own. COEN thrice. We are talking about optical isomers. COEN thrice. Octahedral type की एक पोजीशन बना दो. Octahedral पता है सबको. CO को रखो टेबल पे. दो EN को, I mean you can just place EN the way you want. 6 positions देने के बाद. Just draw it. What will it look like? You will have CO, say, देखो देखो देखो, look at the top. दूसरे स्ट्रक्चर के लिए तो इसमें प्रॉब्लम है ही नहीं क्योंकि हमें मिरर बनाना है और फिर उसकी इमेज बनानी है. So the ones who are good at drawing will be able to do it very well. What do you have here? See, मुझे तो दो पॉइंट्स को ज्वाइन करके EN लगाना है ना, तो ये EN एक, ठीक है, ये मेरा दूसरा EN, ये तीसरा EN. Done? Look onto the board. COEN thrice. दो पॉइंट ऑफ अटैचमेंट सबके, ये बन गया. फैन नहीं है ये, COEN thrice है. ऑलराइट, अब इसका मिरर इमेज अगर मुझे बनाना है तो द मिरर इमेज विल बी, ये EN इस तरफ को है तो मेरा EN ये वाला ये दिख रहा, ये वाला EN ये दिख रहा, सबको दिख रहा है? नहीं दिख रहा शायद. ये वाला EN मिरर के पास है तो मिरर के पास पहले यही आएगा, ठीक है, और ये वाला EN पीछे है. When you look into the mirror, your head is at the back, so head remains at the back in the mirror also. So if EN is here, this EN will be here. Now pick it up and place it on it. Is it superimposable? No. So then that means they are optical isomers of each other because they are forming non-superimposable mirror images. Alright? And one of them will be, what are the types of optical isomers? One of them will be dextrorotatory and the other will be levorotatory. और भी types होते हैं, but अभी के लिए ये करो. Geometrical. That can be done only experimentally. Because dextrorotatory compounds are those, अब इसको याद कर लेना, ये भी पता होना चाहिए, फिजिक्स में भी पढ़ोगे, केमिस्ट्री में भी. Dextrorotatory compounds are those which rotate the plane polarized light to the right. And levorotatory compounds are the ones which rotate the plane polarized light to the left. अब क्या होता है, नॉर्मल रेडिएशन सोर्स पॉलीक्रोमैटिक होती है, फिर हम एक मोनोक्रोमैटर यूज करते हैं. मोनोक्रोमैटर क्या करता है, उस पॉलीक्रोमैटिक रेडिएशन को सिर्फ एक सिंगल वेवलेंथ की रेडिएशन में बना के छोड़ देता है, which is simply a monochromatic radiation, right? That we call it, which moves only in one plane, and we call it the plane polarized light. Now if that is made to fall on my sample, इसका मैं एक liquid solution बना लूँगी COEN thrice का. I will make it available in liquid state. I will put it in a glass tube, the one which is not very sensitive, which is like adaptable to the spectrometer or colorimeter. What we have is plane polarized polychromatic light. एक source से मैंने भेजी, monochromator use करके plane polarized बना लिया. Plane polarized light को मैं अपने sample पे डालूंगी और फिर इधर से हम measure करेंगे कि वो light का whether it is rotating or right. और ये हम measure कैसे करते हैं, डिग्री से, जो मैथ्स में पढ़ते हो. You know how to measure the degrees? What is right angle, 30 degrees, acute, obtuse. So if it moves to the right, then it is like dextrorotatory. If it rotates to the left, then it is levo. The point here that मैंने ये demonstrate क्यों करा, क्योंकि एग्जाम में तो आएगा नहीं, then why did I demonstrate? I wanted to tell you that the approach is interdisciplinary. केमिस्ट्री का मॉलिक्यूल लिया, स्टडी उसको कर रहे हो कि वो ऑप्टिकल आइसोमर कौन सा बनाता है, डेक्स्ट्रो या लीवो. उसके लिए what did you use? The concept of physics. And then finally for measurements you use the concept of mathematics. So basically all things are equally important. So that is why a knowledge is tested from you before the entrance examinations for all the 3 core subjects. English क्यों नहीं पूछते? English is also equally important from personality development. But what is more important for your for all of you all to become engineers in future is that physics, chemistry and math should be absolutely intact. Otherwise you keep talking at all times, so I know that the language will never be a problem for you all. So okay with this? So with this I think I can wrap it up here, right? Here what we have is the types of isomers can be discussed quickly again. We have 2 types of isomers, structural isomers and stereoisomers. Structural isomer वो होते हैं जिसके अंदर हम पूरा बॉन्ड का बॉन्ड ही चेंज कर देते हैं. स्टीरियो में हम बॉन्ड्स एज इट इज चेंज नहीं करते, द बॉन्डिंग रिमेन्स द सेम. जिस एटम की जिस मेटल एटम से बॉन्डिंग होती है वो रिमेन्स द सेम. इस केस में लाइक फॉर एग्जांपल आयनाइजेशन में हम ClNO2 को ही रिप्लेस करा सकते हैं. ये मेरा कोऑर्डिनेशन स्फीयर, Cl बाहर है, NO2 अंदर. आई कैन एक्सचेंज द आयंस फ्रॉम इनसाइड एंड आउटसाइड ऑफ द स्फीयर. Then you have solvate isomerism, that is possible if you have a solvent molecule attached. Then you have or a solvent molecule available as a ligand inside also. That also is a possibility. Structural isomers में the third type coordination should have 2 coordination spheres. Fourth type is linkage. That is linkage बोलते ही what should come to your mind? Ambident ligands, which are of different types. Then you have stereoisomers में you have geometrical isomers and optical isomers. Now when you are talking about geometrical, cis trans is all you remember from your previous studies. Cis trans is possible. That is possible in case of square planar structures or also in case of octahedral like this. ठीक है? Cis मतलब same side, trans means opposite side. Then you can also have facial and meridional, that is FAC and MER. अगर एक ट्राइंगल तीनों साथ में है और एक they are facing each other, then it is FAC, otherwise it is MER. Alright. Then in optical you have again 2 types. One is a dextrorotatory and the other is a levorotatory. That can only be experimentally determined. So exam में इधर L इधर D लिख दोगे तो कोई उस चीज़ का कोई penalty नहीं होगा. So and nobody asks that question because everybody knows that's experimental. Here you can actually form the mirror image and check if the mirror image is not superimposable. It should not be superimposable to show optical isomer. अगर वो superimpose करिए then it is not considered to be an isomer. Then it is not showing optical isomerism. So it has to be not superimposable. So we'll take up questions from this and move on to VBT in the next class. Alright. Thank you. All the best.